So this is a classic energy problem. This bar is initially here with theta equals 30 degrees, and then it's let go and the spring pulls it back up. And so you have lots of things going on here. You have weights at different heights, that's mgh. You have springs at different lengths, that's 1/2 kx squared energy. And then finally ask for velocities, so that will be kinetic energy, 1/2 mv squared and 1/2 I omega squared. So it's definitely an energy problem. And so we start off with figuring out the mass given, 10 kilograms, and the moment of inertia. It's a slender rod, so 1/12 10 times length squared. I'll let you figure out what that is. So when you do any sort of energy problem, you always do a before and after, and you track four things. You track 1/2 mv squared and 1/2 I omega squared, which combine to make the kinetic energy. And you track mgh, that's the potential energy due to gravity, and 1/2 kx squared, that's the potential energy due to the spring. And so for every spring you do 1/2 kx squared, for every body you do an mgh, and for every body you do the kinetic energy. And you do this before and after, and it all adds up before and after, and they're equal. So let's just start. This is released from rest, so the velocity is 0, 1/2 mv squared is 0, and the angular velocity omega is also 0, so 1/2 I omega squared is 0. Okay, so whenever you do a mgh thing, you have to decide the datum, or where you're going to measure 0 from. And so probably the most logical place will be right here. So I'm going to call right at that pin as a datum. And so what you need to do is multiply the weight times the distance it goes up or down from the datum, and the distance of the center of gravity. So the center of gravity of the rod is right in the middle. So if the right end goes down 0.2 meters, the middle, by similar triangles, goes down 0.1 meters. So the kinetic energy is just the weight, which is m times g times the height, 0.1 meters. And in this case, it's going down from the datum, so that's a negative potential energy. There's 1/2 kx squared, and in these problems, they always will give a hint as to what the unstretched length of the spring is. So they do this by either saying, oh, the unstretched length is x meters. And so you take your current length and subtract it from that, and that's how much it stretches. Or there's some kind of clue. So we have to read this carefully. And then it says right here, up here in the problem statement, the spring is unstretched when theta is 0. So when theta is 0, the spring is unstretched. And so right now, the spring has gone down 0.2 meters from theta equals 0. So that means the spring has stretched 0.2 meters. And so it's just 1/2 k, how much it stretches, x squared. Okay, that's before. You add that all up and you set it equal to after. And so after, it will have 1/2 mv squared. And remember, that's the velocity of the center of mass, or the center of the rod. And you'll have 1/2 I omega squared. mgh is 0 because it's back up at the datum. And it says that the spring is unstretched when the rod is horizontal, so 1/2 kx squared is 0. And so we're going to have to do some kinematics to get just one unknown. We have two unknowns, v and omega. And so to do the kinematics, we need to look at the instantaneous center. So here is the rod when it's horizontal, and B is going up because it's in a slot, and A is going horizontal because it's in its slot. And so if you remember, the velocity is the intersection of The distance is perpendicular to the velocities. The instantaneous center is the intersection of the two arms perpendicular to the velocities. So perpendicular to velocity A is this dotted line here. Perpendicular to point B's velocity is this horizontal line. And they intersect right here at A. So A is the instantaneous center. So that means if the velocity, if the angular velocity happens to be omega, the velocity at the center of gravity at the middle is the distance, 0.2 times omega. So this V of the center of gravity is 0.2 omega. Okay, so we can now solve this. You set everything before. Here's the MGH, the 1/2 kx squared equals after 1/2 m, and there we go. V is 0.2 omega squared plus 1/2 I omega squared, and solve for omega. And when you do that, don't forget that when you square 0.2 omega squared, it'll be this. This will be, let me write that. This little piece here, that will be 1/2 m, and you square both of them, right? 0.2 squared omega squared. And then you can factor out the omega squared and you can solve for omega. Okay, that's a typical energy problem.